Let's now consider the association problem. So far we considered a single object and one detection per frame, which we didn't have to associate because we assumed that's the corresponding detection for that object. But in self-driving we typically have to track multiple objects at the same time. And we have many detections in each frame. So the question arises, how can we associate these detections of a new frame to existing object tracks from previous frames? The algorithm for multi-object tracking can be in general outlined as follows. In a first step, we predict objects from previous frames into the current frame, maybe using the motion model. And simultaneously, we also detect objects in the current image. Next, we associate detections to object tracks, and we initiate and delete tracks if necessary. For example, we might need to initiate a track if an object enters the scene. And then we correct the predictions using the observations, for example, using a Bayes filter, as we've discussed previously. Now, how can we measure for the second step, for the association step, that observations in two consecutive frames belong together? There's multiple things that we can look at. For example, we can predict the bounding box via the motion model and measure the overlap with respect to the detections. Or we can compare color histograms or perform normalized cross-correlation between the patches. We can also estimate optical flow and measure the agreement of that, and compare relative location and size of the bounding box, assuming objects don't shrink or grow dramatically between two frames. And we can compare the orientation of detected objects. For example, we could ask an object detector like FastRCNN to also output the heading of the vehicle that is being detected. So this is an overview of some of these very simple association measures like color histogram, bounding box overlap, or orientation similarity. However, we can do better. And what we can do is we can use deep learning, in particular metric learning. The idea here is to use convolutional networks to learn an object representation, f theta, of an image patch I. Here f theta is the neural network with parameters theta that takes the patch as input and computes a feature vector for that patch. Now, what is a good representation? A good representation maps images of the same object to similar features and images of different objects to different features. So for example, in this case, we have a patch that shows this object here, and we call this the anchor A. And we have a positive because this is a patch from a different frame showing the same object. And we have this negative because this is a different object. So what we want effectively is we want to learn a ranking where feature vectors of the same object, A and P, are closer together than feature vectors of different objects, in this case A and N. So we want this to be smaller than this. And we can do this using the so-called and frequently used triplet loss, which is effectively a hinge loss that builds upon this ranking here and tries to enforce that ranking in a soft way. So the hinge loss is defined as the maximum of 0 and this entire expression here, where the first part of this expression is simply this minus this. So we're trying to make like what we just said, the features of the same objects close and features of different objects to be far apart. And then in addition, we have this little margin term m here that ensures that the loss focuses on the difficult cases. What it does effectively is that in the cases where the positive is already much closer to the anchor than the negative, where this condition is already fulfilled sufficiently, we don't create a loss or a gradient because we are clipping at 0 in this case. And so we're making sure that everything that has been already correctly ranked is not considered in the loss function anymore, such that the loss can focus on the difficult cases. And that's really important. It's instructive to actually draw this loss function yourself and see how it behaves to better understand it. I could recommend that. And then there's various techniques on how you can improve training of this triplet loss. For example, typically what is done is using techniques called hard negative mining, where not arbitrary patches are sampled in the image, but we sample patches that are likely to be hard. For example, the black car is clearly different from the white car, but maybe there's more similar but still different white cars that we want to separate. So we want to find those and present those to the learning algorithm. And more recently, there has been a paper by the group of Laura Leal-Terre called The Group Loss for Deep Metric Learning that also tackles the problem of efficient learning for this triplet loss. Still, even having found a good association measure or learned a good feature representation, there is ambiguities, and to illustrate the difficulties in finding the correct association, which is the focus of this unit, I want to show you some of the ambiguities that are present. For example, predictions may not be supported by measurements. And the question in this case is, have objects ceased to exist, or are they occluded, or did detection simply fail? Here's an example. We have a trajectory. This is the prediction, but there's no observation. And the question is, what happened? Similarly, there may be unexpected measurements. Here we have the prediction. None of the detections is close. So what should we do? Are these newly visible objects or just detector noise? Should we instantiate new object tracks? Another case is that more than one measurement may match a particular prediction. So here we have this trajectory with the prediction, and both of these measurements are actually feasible close to that prediction. So which of these measurements is correct? And what about the others? And furthermore, another case that could occur is that a measurement may match multiple predictions. So we have two tracks here, and this blue measurement is actually good for both. So which object shall the measurement be assigned to? The simplest thing that we can do to solve this problem is called nearest neighbor association. In nearest neighbor association, we first of all restrict the measurements to a certain so-called gating area around the prediction. We say, well, if this is the prediction, then we want to only consider object detections that are nearby, because things that are very far, we believe, are unlikely to correspond to that track. And green is the gating area here. So all of the detections that are outside of the gating area have been masked now. And then we can associate a detection from the set of detections calligraphic y at time t that is closest to the prediction. So for example, in this case, this would be this detection here. Mathematically, this can be formulated as the argmin over all yt, minimizing the L2 distance between yt and xt. Or alternatively, it can be written like this. Better even is if we have a motion model, like for example in the Kalman filter, we have a Gaussian prediction model, remember? So if we have a Gaussian prediction model, as an example, then we can consider the detection that is most likely under that prediction model, the one that maximizes the likelihood under that prediction model. And this corresponds to the so-called Mahalanobis distance, which is basically what is in the exponential of the Gaussian distribution here, with the covariance matrix in the middle. So instead of just taking the closest prediction in L2 sense, we can now take the closest prediction in terms of this ellipsoidal non-isometric distance based on this covariance matrix. And a nice thing about this Mahalanobis distance is that it can also be used to define the gating area, of course, right? So we can use that, we can threshold the Mahalanobis distance that's given to us through the prediction model, because this is something we have estimated through the Kalman filter. We can use that to threshold the gating area. Now, what's the problem with this simple approach? Let's consider a very simple example with two objects, blue and red, that move like this. Of course, we don't know that the blue object is the blue object and the red object is the red object. So there's like, we can associate this object with this one or this object with this one, and vice versa here. Now let the numbers here represent association scores, where higher scores means they are more likely to be the same. So for example, in terms of distance or following the motion model, they are, these two are more likely to be associated than these two, because they are, this one is further apart from the prediction of this object track than this one. So in this particular case, it's clear that these two should be associated and these two should be associated. That's something that nearest neighbor association would do for us. But let's consider a more tricky situation now, where we go one step further, one frame further. Now in this case, it's much more ambiguous. For example, considering the location, the predicted location, as a similarity measure. And choosing the nearest neighbor here would fail. For example, for the red object, we would choose the blue prediction, which has a higher similarity score than the red one. And so in this case, we would even consider this detection twice, once for the blue track and once for the red track. And in practice, the situation may be much more severe, much more difficult. There's much more detections. Detections are noisy. And the question is when to continue, start, or kill a track. I hope this illustrates that a simple nearest neighbor approach is in general not a good idea. So how can we go beyond that? And the answer to this is bipartite graph matching. We're effectively exploiting tools from the graph theory community in order to help us here. Given a bipartite graph as illustrated here, a matching is a subset of the edges for which every vertex belongs to exactly one of the edges. Now let's first digest this sentence. This is a bipartite graph. Why? It's a graph that comprises nodes and edges. And the edges are only between nodes of different sets. We have one set here, frame t, and one set here, frame t plus 1. And there's only edges between the sets and not within the sets. And that's why it's called a bipartite graph. Now in this particular bipartite graph, a matching is one that is a subset of all of these edges, for which every vertex belongs to exactly one of the edges. For example, a matching is the one that's highlighted here in red. For this matching, for this selection of edges, for this subset of edges, there's only, every vertex belongs to exactly one of the edges only. Now you see already where this is going probably, right? Frame-to-frame tracking can therefore be formulated as bipartite graph matching, which, by definition of this problem, chooses at most one match in each row and column of such a similarity matrix while maximizing the score. So here we have exactly the same situation. Now we have three objects. These are the tracks. Here we have the detections in the next frame. And these are the similarity scores. And of course, we want to associate every of these object tracks to only one detection and vice versa. In other words, there should be only one association made per row and per column, as in this example here. And the solution that's highlighted here in red is the one that maximizes the total score. And that's what we want to do. We want to maximize the sum of these numbers for such a bipartite graph matching. For example, if we would choose the diagonal, which would also be a valid match, we would have a smaller sum than for this particular configuration, for this particular association here. And this particular association actually corresponds to the matching that's illustrated here on the left. The first object is associated with the second detection. The second object here is associated with the third detection, and so forth. So you can see now how this association problem in tracking boils down to a bipartite graph matching problem. Now the question is, of course, how can we solve this bipartite graph matching problem? And that's what we're going to discuss now. Let's first formally define it. Assume n detections in the previous and m detections in the current frame. We can then construct a m by n table of matching scores. Before we had a table of 3 by 3, now we have a table of 5 by 5. 5 object tracks, 5 detections in the current frame. And the task is to choose a 1 by 1 matching that maximizes the sum of scores. So what is the optimal 1 by 1 matching? If you look at this table, it's not so obvious, right? I think you would need to try a little bit and play with these numbers, subject to the constraints that we have, in order to find the optimal matching, even for it's a very simple case. So let's more formally define the bipartite graph matching problem now. Given an m by n matrix of association scores S, determine a binary m times n matrix C that maximizes the total score. So we want to find the argmax of the sum over all rows and columns of the elements of these two matrices multiplied together, subject to the constraint that in each row and in each column of this binary matrix C there is exactly one element 1 and all the others are 0, and also subject to the constraint that the elements of the binary matrix are actually binary. This is an integer linear program, or ILP in short, which in general is NP-hard, but luckily in this particular case it's not. There is polynomial time algorithms for solving it. And these constraints here ensure that we can only choose one number from each row and from each column. So we want to find a 1-to-1 matching. That's what we discussed here, right? So we don't want to match this track to 2 detections, but just to 1. We don't want to match this detection to 2 tracks, but just to 1. Okay? So this is just the definition, the setting, the problem setting. The question is, of course, how to solve it. First of all, how many different assignments are possible? Well, there is n factorial possible assignments. So in the case of 5 by 5, we have 5 factorial, which is 120. For the first object track, we can choose 5 object detections. Once we have made that choice, we can choose amongst 4 remaining ones. And then for the third one, amongst 3, and so on. So 120 is already a lot, but in practice, we often have to deal with much more detections. And so exhaustive search really becomes intractable. So we need something better than just brute force searching through all of these assignments that are feasible. And the simplest one, the simplest algorithm is called a greedy algorithm. And it's very simple. We start with an unmarked matrix, and then for I equals 1 to n, we mark the largest value that isn't in a row or column with already marked entries. And that's it. So let's look at an example. We take this matrix of similarity scores and we find the maximal value in there, because we believe that's a good matching. Or that's a good association. So we associate the object track 1 with detection 1 in frame T. And then, because we don't want to select any of the elements from that corresponding row and column, we strike these out. Now we find the second one, which in this case is 0.94. We mark that one and we remove the row and the column respectively. So you can implement this simply by manipulating a matrix. It's really easy. And then we find the third match and remove rows and columns. The fourth one, and then this one here remains. And this is the greedy solution. And the greedy solution is often okay. Greedy matching is easy to implement, quick to run, and finds good solutions. In this case, the overall score obtained is 3.77. However, greedy matching often doesn't yield the optimal solution. In this particular case, there's quite some margin to the optimal solution, which is 4.26 and illustrated here. This is the optimal solution to this particular instantiation of the problem. How can we find the optimal solution? As mentioned before, there is luckily algorithms in the graph community that can solve this for us optimally in polynomial time. One of the earliest methods is called the Hungarian method, and it has quadratic complexity. And a little bit later, Ford Fulkerson proposed an algorithm with only cubic time complexity. And so these algorithms can deliver solutions fast, and that's why they are frequently used for frame-to-frame tracking or bipartite matching. Now, we're not going to go into the details of these algorithms. They are quite technical and require some knowledge from graph theory, but I pointed out to you the original paper from Kuhn called the Hungarian method for the assignment problem. Now, one thing we didn't discuss, right? We assumed there's 5 object tracks and 5 detections, but of course, typically there will be a different number of tracks and observations, and also object tracks may end. There may be not a detection or start. There may not be an existing track to match against. And such an example is shown here. This is the optimal solution for this particular situation where we have 4 tracks and 4 detections. And you can see that for track 1 and detection 1, we have a pretty high similarity, and also for track 2 and track 4. But for track 3, none of the objects is really a plausible detection for that object. Yet, of course, our solution to that original problem that we formulated here doesn't care about this. It just maximizes the score, and so it associates this as the final association here, this value here, because it adds the overall, it adds 0.06 to the overall score. Now, this is not what we want, because in this case, it's actually very likely that track object detection 3 is not the detection that corresponds to track 3, but rather track 3 probably has ended, and maybe object detection 3 is starting a new track. So what can we do in this case? And there's a simple trick here. And the trick is to use exactly the same algorithm as before and the same formulation, but to introduce extra nodes that absorb these matches with a value threshold, in this case 0.3. What happens now is that for object track 3, we are associating this extra node, not this object detection 3 with a very low score, but we are associating this extra node, which means for our solution that the object track 3 has actually stopped. We have associated it into this absorption node. And we can solve this problem with the augmented matrix exactly the same way as before with the Hungarian method, for example. And it allows us to end object tracks or to start new object tracks. Now, this was all about frame-to-frame matching. Bipartite matching is only able to match detections to, like in the current frame, to object tracks in the previous frame, or to detections in the previous frame, or to predictions of tracks into the current frame. But this is not necessarily optimal. So we have seen how we can solve the association problem for 2 frames. It's not necessarily optimal for longer sequences. In particular, wrong associations cannot be undone at later frames. We might commit to something that's actually, it's going to turn out later on, it's not the right thing to do. So let's now look at the multi-frame case. And the setting is tracking by detection as before. And the goal is to solve for all associations across all frames of a sequence. And of course, this is again the batch mode that in the first place is not interesting for self-driving, but there is online versions of this algorithm as well. The seminal idea that was presented in this paper from Zhang et al., called Global Data Association for Multi-Object Tracking Using Network Flows, is to cast the problem as a min-cost flow network problem. So to again, like just phrase the problem such that it can be applied to existing algorithms in the graph community. And this is the way they formulated the problem. The idea is to have each detection create 2 nodes in the graph. So this is one detection at time 0, and this is another detection at time 0, and so on. And then to connect these 2 nodes of a detection with an edge that carries a negative cost proportional to the detection confidence. In addition, we associate these detections to detections in the next frame, and we associate the first, or we connect the first node of a detection to the source of that graph, S, and the second to the sink. And what we are then going to do is we are going to try to push so-called flow from the source to the sink such that the cost along the edges overall is minimized. And that's why it's called a min-cost flow problem. And in this case, the observations, they carry negative costs, so the flow is encouraged to pass through the highly confident observations, and the transition edges carry positive costs to separate dissimilar objects. And if an edge carries a small positive cost, then it's likely to be traversed because there's maybe another detection coming afterwards that has a negative cost that we want to, push the flow through. And as you may note, by this formulation, we can now handle multiple frames, shown our 3 frames here, but can handle much larger sequences. And we can automatically determine when a track starts and ends, because it starts where we have a flow that goes from S to the first detection, and it ends where maybe here the second node of the last detection has a flow to the sink, because there's constraints that the flow can always be just 0 and 1, and if there is an outgoing flow from that node to the sink, then there can be no flow to any other nodes. So I'm not going to go very much into detail. This is just very generically the formulation of this problem. We have these binary flow variables f that can be 0 or 1, and there is these costs at each edge. So there's a flow variable and a cost variable at each edge. And there is entry costs, costs for starting a track. There's exit costs, cost for ending a track. And there is link costs and detection costs. Detection costs are these are the negative ones, and the link costs are these, which are the positive ones. And in addition, we have these constraints here, which are the flow conservation constraints, which ensure that there's no overlapping object trajectories. This is what I just mentioned. If there's a the flow that's entering, so the flow that's entering to a node that can be 0 or 1, plus all the flow that's coming in from previous nodes, must be the same as the flow that's going through that detection. And that must be the same as the flow that exits from here and the flow that leaves that node towards detections in the next frame. All right? So this is the high-level intuition of this formulation. The optimal solution of this problem can also be found in polynomial time through an algorithm that's called the successive shortest path algorithm. Actually, in the original work, Zhang et al. Didn't use that algorithm, but in later works, it has been found to be the fastest algorithm for this problem. However, we are only able to model pairwise relationships with this algorithm. You may have noted that we have only like these pairwise edges between adjacent time steps. So we can not model any occlusions, or we have to link detections across multiple frames, which becomes computationally expensive. And we can only use very simplistic motion models like the object is not moving far, is like constant position model. So these are the disadvantages of this first formulation. And another disadvantage is that it has to process in batches, but there's online versions that have been proposed. For example, the one here by Lenz et al. So here's an example of what this looks like. So here you can see the tracking result. The boxes are flickering because we haven't, like, this is results that have been obtained just through association of raw detections, and there hasn't been any filtering applied to these detections. So that's why they look flickering. Now let's, in the end of this unit, look at two more advanced graph-based models and also at evaluation of multi-object tracking. So one advanced model that has been proposed at ICRA 2018 is training, detection, and tracking jointly, which is of course a good idea, right? In the previous model, in this flow model here, we are typically training first, like we're doing metric learning, and we're training the object detectors independently of solving this optimization problem. But ideally, you train everything jointly end to end, and that has been demonstrated to be actually possible in this paper. I like this paper quite a lot. By backpropagating through a linear program that solves this task. This min cost flow problem can be solved also by a linear program. So they show that you can backpropagate through this linear program. Consider this as a layer in a neural network. And so you can backpropagate through the detection network as well to update the parameters end to end. And another more recent idea that has achieved state-of-the-art results is actually much simpler. It's realizing that basically we have a graph-based problem here, and if you have attended my computer vision lecture, you've seen that there has been great advances in graph neural networks in the last decade. And so of course it's natural to ask, can't we just directly solve this problem using graph neural networks? And it works quite well. So in this case, the input is encoded using convolutional neural networks into features. And then these feature encodings are processed with neural message passing on that graph. And the problem that's formulated is a simple edge classification problem where edges that are associated to the same track are classified positively. So very simple, straightforward to implement with today's frameworks, and easy to train because it's all end-to-end differentiable. Now finally, let's talk about how we can evaluate multi-object tracking. And the first step that we have to do when we evaluate multi-object tracking is to associate predictions with ground truth tracks. And that's done similarly to evaluating object detectors using bipartite graph matching. So here are 4 different examples. At the bottom you can see the different time steps. And if we look, for example, at the first situation, we have the ground truth here in dashed lines. And then we have 2 predictions, red and blue. And we have associated them using bipartite graph matching. So the red one has been associated such that, well, these 3 nodes are associated to these ground truth nodes here, and the blue one such that these 2 blue nodes are associated here. But these nodes are not associated because they are either too far from the ground truth indicated here by this gray corridor, or because, like, the other node was a better match. And so if a circle is non-filled and colored, it's a false positive. It's a false positive detection. And if a node of the ground truth is not filled, it's a false negative because it hasn't been detected by any of these tracklets that have been predicted, these tracks, these trajectories. Yeah, and so these are different situations for different ground truth and object track predictions. So the first step is to associate predictions using some graph matching technique, and that's also the algorithm that's running on the server, for example, on the mod challenge server or on the KITTI evaluation server for evaluation. And then by far the most prominent and oldest metric to evaluate tracking, which is not an easy task, is called MOTA, which is called Multiple Object Tracking Accuracy. And what it does is it produces a number that's 1 minus this expression here, where t is the index over the time dimension over all the frames. And we're counting the false negatives and the false positives and the ID switches. An ID switch is if a ground truth trajectory is tracked by one object and then suddenly by another one. So we are switching effectively the ID. We are not recovering that this is one single identity, but we are finding two different tracks. So these are all things that we don't want. So we're counting them as errors, and we're dividing this with respect to the total number of detections, which is gt at time t. So a very simple measure, but it has also many flaws. And a more recent measure that avoids some of these problems is called HOTA, and it's also implemented in the state-of-the-art evaluation frameworks, a higher order metric for evaluating multi-object tracking that works quite differently from this one here. So state-of-the-art algorithms are evaluated on benchmarks where participants can submit their results on held out test data. They get their evaluation results and get ranked. And one of these benchmarks in the self-driving domain is called the KITTI benchmark. And it has also, amongst other benchmarks, for example, for stereo and flow, scene flow, or odometry, or object detection, it has a benchmark for object tracking. And so if you're curious, you can look at the leaderboard, which is linked here.